contrast to the spin echo sequence, the inversion recovery sequence uses first a 180-degree pulse, which is then followed by a 90-degree pulse. What happens? The 180-degree pulse turns the longitudinal magnetization in the opposite direction. All protons that were responsible for the net magnetic moment pointing up now point down. If we do not do anything else, the longitudinal magnetization will slowly go back up, like a ball that is thrown into water. To get a measurable signal, however, we need some transversal magnetization. And for this, we use the 90-degree pulse. So, we first use a 180-degree pulse, which turns the longitudinal magnetization in the opposite direction, which is then followed by a 90-degree pulse. The 90-degree pulse tilts the magnetization into the transversal XY plane so it can be measured, received. Similar to the spin echo sequence, we use several pulse cycles for signal measurement. Let us now compare two tissues with a different T1. Before the 180-degree pulse, there is no difference. After the 180-degree pulse, we can see that tissue B goes back to its original longitudinal magnetization faster, thus has the shorter T1. After the 90-degree pulse, we can measure, receive the new transversal magnetization, which in this example is less for tissue B with the shorter T1. The signal that we get depends on the time between the 180-degree and the 90-degree pulse, the time after the inversion by the 180-degree pulse. This time is thus called Ti, inversion time. Tr is the time between the sequences, as in the other pulse sequences. The signal intensity in an inversion recovery image is thus dependent on T1, which determines how fast the longitudinal magnetization goes back to its original value. So we get a T1-weighted image, which is even more T1-weighted than partial saturation recovery images.